Hi everyone, welcome to this course on the Python NumPy library. If you want to work with data efficiently in Python, then NumPy is a skill you absolutely must learn. NumPy is the foundation for data science, machine learning, scientific computing, and many advanced Python libraries. In this course, we'll start from the basics with a clear introduction to NumPy and learn how to create arrays the right way. Then we'll move step by step into array indexing, slicing one-dimensional and two-dimensional arrays, and understanding NumPy data types. You will also learn how to work with array shapes, reshape arrays, iterate through data, join and split arrays, search and sort data efficiently, and filter arrays based on conditions. Everything is explained with simple examples so you can follow along easily. By the end of this course, you will be confident using NumPy for real-world data problems. Let's get started. Hi everyone, welcome back. In this lecture, we are starting a brand new journey into one of the most powerful libraries in Python called NumPy. If you are learning data science, machine learning, artificial intelligence, or scientific computing, NumPy is absolutely essential. So what exactly is NumPy? NumPy stands for Numerical Python. It's a Python library used for working with arrays, especially multidimensional arrays. But it's not just about arrays. NumPy provides a wide range of mathematical, statistical, and linear algebra operations that are optimized for performance. Here's why NumPy is so important. Let's say you are working with a huge dataset, like thousands or even millions of numbers. Using plain Python list will be slow and memory heavy, but with NumPy arrays, the same operations become faster, more efficient, and use less memory. It's the backbone of many other libraries like Pandas, scikit-learn, TensorFlow, and more. These libraries internally rely on NumPy for mathematical operations, so learning NumPy is a must for any serious Python developer in the data world. Now let's talk about the core feature of NumPy. It introduces a new data structure called the ND array or n-dimensional array. This is way more powerful than regular Python lists. Why? Because it supports element-wise operations, vectorization, broadcasting, and more. Now, before we can start using NumPy, we need to make sure it's installed. Let's open PyCharm. Go to your terminal or command line. Type the following command. We type pip install numpy. This command will download and install NumPy from the Python package index. Once installed, we are ready to use it in our programs. Next, you can import and use this library in Python. We will see how to import and use NumPy library in next lecture. Now here's something important. NumPy is written in Python, but internally it uses C and C++ for performance. That's why NumPy is much faster than Python lists, especially for large data operations. Let's now talk about some real things NumPy can do. It allows you to perform mathematical operations on entire arrays without writing loops. For example, you can multiply all elements in an array by 10. In just one line. It also supports operations like summing values, finding max or mean, sorting, filtering, reshaping arrays, slicing, matrix multiplication, and more. NumPy arrays are homogeneous, meaning all elements are of the same data type, like all integers or all floats. This gives it a performance advantage compared to Python lists, which can hold mixed types. Now let's summarize why NumPy is important. It's fast, it's memory efficient, and it's used everywhere in the Python data ecosystem. From small personal projects to huge data science pipelines, NumPy is at the core. So if you are serious about learning data science or doing any kind of numerical computing, start with NumPy, master it, and build a strong foundation. That's it for this theory introduction. In the next lecture, we'll jump into hands-on coding and see how to create NumPy arrays using various techniques. So open your editor, install NumPy if you haven't already, and get ready for some coding action. See you in the next lesson. Bye for now. Hi everyone, welcome back. In the previous lecture, we learned what NumPy is, why it's used, and where it's applied. In this lecture, we're going to learn step by step how to create NumPy arrays in PyCharm. We'll cover arrays from lists, tuples, different dimensions, and even higher dimensional arrays. Let's begin. First, let's open PyCharm, create a new folder called NumPy. Right-click on the NumPy. Choose New, then Python file. Let's name it NumPy _ creating _ arrays. Now, at the very top of the file, we type import NumPy as NumPy. This means we are importing the NumPy library and giving it the short alias np. This alias is a community convention. It makes our code shorter and easier to read. Let's now create our first array from a Python list. We type a variable named numbers _ list _ array equals followed by the alias np dot called an array function, and inside the parentheses we pass a list square bracket 10, 20, 30, 40, 50 square bracket close. This list contains 5 numbers, and NumPy's array function converts this entire list into a powerful NumPy array object. This is the most basic way to create an array in NumPy. You just take your Python list, wrap it inside the array function, and you are done. Now below that, type print open parenthesis numbers _ list _ array close parenthesis. Below that again, type another print line, print open parenthesis, type open parenthesis numbers _ list _ array close parenthesis twice. Let's now run the program. The output will display the numbers 10, 20, 30, 40, 50. And below that you will see class numpy.inadArray. That means our regular Python list has been successfully converted into a NumPy array. It now supports advanced math operations, better performance, and less memory. Now let's do the same thing but using a tuple. We type numbers _ tuple _ array equals np.array, and this time inside the parentheses we pass a tuple round brackets with values 10, 20, 30, 40 and 50. Notice that we are using round brackets to create a tuple. List uses square brackets. Then type print within parentheses numbers _ tuple _ array. Let's run this part now. The output looks the same 10, 20, 30, 40, 50 because NumPy treats tuples and lists the same when converting to arrays. Using tuples is helpful when your data is fixed and should not change since tuples are immutable. Let's now create a scalar or a zero-dimensional array. We type single _ value _ array equals np.array and pass one number like 99. Then type print within parentheses single _ value _ array. Let's run the program now. You will just see the number 99. Even though it looks like a regular number, internally it's stored as a zero-dimensional array. This is useful when performing operations on single values that need to be treated as arrays. Let's now create a one-dimensional array, like a row of student scores. We type student _ scores _ array equals np.array and pass a list 80, 85, 90, 95 and 100. Then print the variable print student _ scores _ array. Run it and you will see all 5 numbers displayed in a straight line. This is a one-dimensional array, the most common and basic form in NumPy. It's great for handling sequences, math vectors and time series data. So far, we have created simple one-dimensional arrays, but real-world data often looks like tables with the rows and columns. That's where two-dimensional arrays come into play. You can think of a two-dimensional array like a spreadsheet or a matrix, rows stacked one after another, and inside each row we have columns. Now let's create a two-dimensional array. We will give it a variable name called matrix underscore table underscore array. We set it equal to NumPy's array function. Inside that we provide two lists. The first list contains the values 1, 2 and 3. The second list contains the values 4, 5 and 6. So the full line will create something like this. One row with numbers 1, 2 and 3. Another row with numbers 4, 5 and 6. Together, these two rows form a proper two-dimensional matrix. Now let's print the array to see how it looks. We use the print function and pass our variable matrix underscore table underscore array. Let's run the program and check the output. This is NumPy's representation of a 2D array. Notice how it is structured. The first square brackets enclose the entire matrix. Inside we see two rows. The first row has values 1, 2, 3. The second row has values 4, 5, 6. This array has two rows and three columns. That means its shape is 2 by 3. We can verify this using the dot shape property of the array. If we print matrix underscore table underscore array dot shape. Next, run the program. The output will be 2, 3. This means 2 rows, 3 columns. This is the foundation of working with two-dimensional arrays in NumPy. They allow us to represent data in tables, grids or matrices, which is extremely useful in mathematics, data science and machine learning. So far, we have worked with one-dimensional arrays, which are like a simple list of numbers, and we have also worked with two-dimensional arrays, which are like a matrix with rows and columns. But a three-dimensional array takes this to the next level. You can think of it like a cube of data. Just imagine a Rubik's cube where numbers are arranged in layers. That is what a 3D array looks like in NumPy. Now let's actually create our 3D array. We'll store it in a variable called cube underscore data underscore array. So we type cube underscore data underscore array equals np dot array followed by parentheses. Inside these parentheses we are going to define nested lists. The first inner list will be square brackets containing the numbers 1, 2 and 3. Then another list containing the numbers 4, 5 and 6. That gives us one layer. The second inner list will be exactly the same. So another set of 1, 2, 3 and 4, 5, 6. When combined together, this structure represents two layers. Each layer has two rows and each row has three elements. So in total, our three-dimensional array has two layers times two rows times three columns. Now let's print it. We type print and inside the parentheses we put cube underscore data underscore array. Let's now run the program and see the output. When we execute the script, Python prints the three-dimensional array in a structured way. You will see the numbers arranged in two separate blocks 1, 2, 3, 4, 5, 6 and then another block right below it with the same values. This shows that NumPy has created a cube-like structure where the data is stored in 3 dimensions. Notice that the output uses multiple brackets. The outermost bracket represents the cube itself. The second level brackets represent each layer, and the innermost brackets represent the rows inside each layer. This is how NumPy neatly displays 3D arrays. Now you may ask, why do we need 3D arrays? Well, they are extremely useful when working with data that has multiple dimensions. For example, in computer graphics, images are stored in 3 dimensions, width, height and color channels. In scientific computing, you may represent measurements that vary over time across different sensors and in multiple categories. So 3-dimensional arrays give us the ability to represent complex data in an organized way. And NumPy makes it very easy to create and manipulate them. So let's quickly summarize. we created arrays from both lists and tuples. We explored 0-dimensional, 1-dimensional, 2-dimensional and 3-dimensional arrays. Thanks for watching and I'll see you in the next one. Hi everyone, welcome back. In the last lecture, we learned how to create NumPy arrays using different techniques from simple lists to multi-dimensional arrays. In this lecture, we are going to learn one of the most important concepts in NumPy, indexing. Indexing means accessing individual elements of an array, just like you do with Python list. But in NumPy, it works across multiple dimensions, 1-dimensional, 2-dimensional, and even 3-dimensional arrays. Let's begin. Open PyCharm and create a new Python file. Let's name it numpy_array_indexing. Now at the top, let's import NumPy. We type import NumPy as np. Let's start by creating a simple 1-dimensional array. We type scores_array equals np.array and inside square brackets we pass 10, 20, 30, 40, 50. This creates a 1-dimensional array of scores. Now print it so we can see the full array. Let's run this. Output will show 10, 20, 30, 40, 50. Now let's try to access a specific element. In Python, indexing starts from 0. Let's print the element at index 0. We type print within parentheses scores_array, then within square brackets pass the index 0. Let's run it. Output will be 10. That's the first value in our array. Let's now try the third item. Change the index to 2. Run again and you will get 30. Because index 2 means the third position, you can also access the last element by using negative indexing. We type print within parentheses scores_array, then within square brackets pass the -1. Run the program again. It will print 50, the last item in the array. NumPy allows negative indexing for its array. The index of -1 refers to the last item, -2 to the second last item, and so on. Try square bracket -2. We type print within parentheses scores_array, then within square brackets pass the -2. Run the program again. It will print 40, the second last item in the array. Perfect. Let's now create a 2-dimensional array, like a table of student marks. We type marks_matrix equals np.array. Inside we pass 2 rows. First row 90, 85, 80. Second row 70, 75, 65. Each row is wrapped inside square brackets, and both rows go inside a larger pair of square brackets. Now print the matrix. Let's run the program. The output will look like this. First row 90, 85, 80. Second row 70, 75, 65. This is a 2-row 3-column matrix. Let's now access values from this 2-dimensional array. To access a specific item, we need to give both row index and column index. If we want the very first element, which is 90, we use row index 0 and column index 0. We type print marks_matrix within square brackets 0, 0. Run it. Output will be 90. That's the value at row 0, column 0. If we want the middle value of the first row, which is 85, we use row index 0 and column index 1. We type print marks_matrix within square brackets 0, 1. Run it. Output will be 85. That's the value at row 0, column 1. If we want the last value of the first row, which is 80, we use row index 0 and column index 2. We type print marks underscore matrix within square brackets 0, 2. Run it. Output will be 80. That's the value at row 0, column 2. If we want the first element of the second row, which is 70, we use row index 1 and column index 0. Let's type print marks underscore matrix within square brackets 1, 0. Run it. Output will be 70. That's the value at row 1, column 0. If we want the middle element of the second row, which is 75, we use row index 1 and column index 1. Let's type print marks underscore matrix within square brackets 1, 1. Run it. Output will be 75. That's the value at row 1, column 1. And finally, if we want the last element, which is 65, we use row index 1 and column index 2. Let's type print marks underscore matrix within square brackets 1, 2. Run it. Output will be 65. That's the value at row 1, column 1. You can also extract an entire row. Just use one index, square bracket 0. That gives the full first row. Run it. And you will get full first row. Now let's see how to create and access elements from a 3-dimensional array in NumPy. Now we'll first create a 3-dimensional array. Let's give it a variable name cube underscore data underscore array. We say cube underscore data underscore array equals np.array. Then open triple square brackets to define a 3D array. Inside the first layer, we define two rows. The first row is 1, 2, 3. The second row is 4, 5, 6. Then we define the second layer again with two rows. The first row is 7, 8, 9. The second row is 10, 11, 12. Altogether, this creates a 3-dimensional array with two blocks, each block having two rows and 3 columns. Now let's display the entire array. We say print and pass in cube underscore data underscore array. This will show us the full structure of the cube, two separate blocks with their rows and columns. Let's now run the program and see the output. Two blocks, each block having 2 rows and 3 columns. This confirms that we have created a 3D structure with 2 layers, and each layer contains 2 rows with 3 elements. Now let's access individual elements using index positions. Remember, indexing starts from 0 in Python. Let's start with the first element in the first row of the first block. We say print followed by cube underscore data underscore array with square brackets containing 0, 0, 0. That means block 0, row 0, column 0. Let's now run the program and see the output. This gives us the number 1. Let's now access the third element in the second row of the first block. We say cube underscore data underscore array with indices 0, 1, 2. That's first block, second row, third element. Let's now run the program and see the output. This gives us the number 6. Next, let's access the second element of the first row in the second block. We type cube underscore data underscore array square brackets 1, 0, 1, block 1, row 0, column 1, which gives us the number 8. And finally, we'll access the last element in the last row of the second block. That's block 1, row 1, column 2. Let's now run the program and see the output. This gives us the number 12. This shows us how we can precisely navigate a 3-dimensional NumPy array by using 3 index values, one for the block, one for the row, and one for the column. Thanks for watching, and I will see you in the next video. In this lecture, we will learn slicing one-dimensional arrays. Let's start with a quick explanation. Slicing in Python means taking elements from one given index to another given index. Instead of accessing just a single element using an index, slicing lets you extract a portion of the array. We do this by using square brackets and colons. And here are some defaults you should remember. If you don't provide a start index, it's considered 0. If you don't provide an end index, it's considered the length of the array. And if you don't provide a step, it's considered 1. Let's get started. Open your PyCharm IDE. Right-click on the NumPy folder. Choose New, then Python file. Let's name it numpy_slice_1d. At the top of the file, let's import the NumPy library. We say import NumPy as np. This gives us access to all NumPy's powerful array tools. Let's create a basic one-dimensional array. We name it scores_array. We assign it to np.array and pass in a list of numbers. Let's use 10, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. This array could represent test scores or sensor readings. Now print the array. Print scores_array. Let's run the program. You can see all the numbers printed in a single row. This is our 1D array. Let's now slice a portion from this array. We'll use the syntax start index : end index. Remember, the start is included, but the end is excluded. Let's extract values from index 2 to index 5. That means elements at positions 2, 3 and 4. We create a new variable called sliced_array. Assign it to scores_array, then use square brackets with 2:5 inside. Now print this new array. Print sliced_array. Let's run the program. The output will be 30, 40 and 50. You'll see index 2 gives 30, index 3 gives 40, index 4 gives 50, index 5 is excluded. This is the basic behavior of slicing with colon in NumPy. What if we want to start from the beginning of the array? We can skip the start index and just write :end print within round brackets scores_array within square brackets :4. That means start from index 0, go up to 4, excluding 4. Let's run the program. This gives 10, 20, 30, 40. Perfect. We see the first 4 elements. Now let's try slicing to the end. We skip the end index and only give a start like 5 : This means start from index 5 and go all the way to the last element. We print scores_array square brackets 5 : Let's run the program. The output will be 60, 70, 80, 90, 100. These are last 5 elements of the array. Let's try slicing the full array using just a colon. This is like copying the full array. Type print within round brackets scores_array within square brackets : Let's run the program. The output will be the same as the original array, from 10 to 100. This is helpful when you want to copy the array without changing the original. Let's try slicing with a step value now. We want to slice the array with a step size of 2, meaning we skip one element every time. Let's type print within round brackets scores_array within square brackets : 2. What does this mean? We have left the start and end blank, so it includes the whole array. But by giving :2, we are telling Python to pick every second item. Let's run the program. Because it starts from 10, skips 20 includes 30, skips 40 includes 50, and so on. This is very useful when you want to grab alternate elements from an array. Now let's try with step size of 3. This time we want to pick every third element from the array. Type print within round brackets scores underscore array within square brackets colon 3. Again the start and end are blank, so we include the whole array. But with step 3, it jumps ahead by 3 elements every time. Let's run the program. It starts from 10, skips 20 and 30, includes 40, skips 50 and 60, includes 70, and so on. This pattern is great when you want to reduce the sampling rate in a fixed step pattern. It works the same way for strings or lists too. Let's now try slicing using negative index values. In Python, negative indexes start from the end. -1 means the last item, -2 means second last, and so on. We want to select the last 3 elements of the array. Type print within round brackets scores underscore array within square brackets -3 colon. Here -3 means the third last item, and since the end is blank, it goes till the end of the array. Let's run the program. The output, you can see last 3 items. This is especially useful when you are only interested in the tail part of the data. Now let's try a more custom range using negative indexes. We want to slice from the 5th last item to the 2nd last item. Type print within round bracket scores underscore array within square bracket -5 colon -2. Let's decode that. -5 points to the 5th last element, which is 60. -2 points to the 2nd last element, which is 90. But remember, slicing excludes the end, so it will stop before 90. Let's run the program. These are the items from index -5, -4, and -3. This kind of slicing is great when you need a specific portion of data from the back of the array without calculating the actual positive indexes. This is all about slicing one-dimensional arrays using NumPy. In this lecture, we're going to learn how to slice two-dimensional arrays using NumPy. Slicing means getting a part of the array by specifying a start and end. The basic syntax is array name, square brackets, then 2 slices, one for rows and one for columns. Like this, array name, square brackets, row slice, comma, column slice. If we write 0, 2, 1, 3, it means pick rows from index 0 to 1 because end is not included, and columns from index 1 to 2 because end 3 is not included. Let's now see this practically step by step. Right click on your NumPy folder, choose new and select Python file. Let's name it NumPy underscore slicing underscore 2D. Now let's begin writing our code. First let's import the NumPy library. Import, that's the keyword. Then type NumPy, all lowercase. Then type as followed by the letters NP. This lets us use the shortcut NP every time we use NumPy functions. Let's now define a two-dimensional array and give it a readable name. We'll call it table underscore data underscore array. Type table underscore data underscore array equals np dot array. Then open a pair of parentheses. Inside this, we'll pass a list of lists, one for each row. Let's type 4 rows like this. First row, open square bracket 10, 20, 30. Then close square bracket. Second row, open square bracket 40, 50, 60. Close square bracket. Third row, open square bracket 70, 80, 90, close square bracket. Fourth row, open square bracket 100, 110, 120, and close. All these rows are enclosed in one outer square bracket, so your entire line becomes a list of lists which represents a table. This is what we call a 2D array with 4 rows and 3 columns. To display the array in the console, just type print within parentheses table underscore data underscore array. That's it. Now let's run the program. You will see this output 10, 20, 30, 40, 50, 60, Now 70, 80, 90. As 100, 100, 10, 100, 20. Each line represents a row in the table. Each number is a column value in that row. The outer square brackets show that this is a two-dimensional structure. This kind of array is great for storing tabular data like student marks, inventory, or pixel grids in images. Now we'll slice only the first two rows of the array. We type print table underscore data underscore array square brackets 0 colon 2 comma colon. Let's break that down. 0 colon 2 means we are selecting from row index 0 up to but not including row index 2. So we get row 0 and row 1. The comma colon means we are including all columns for those rows. Let's run the program. You will see 10, 20, 30, now 40, 50, 60. Perfect. We got the first two rows with all columns included. This is helpful when you want to examine the top part of a dataset. Next, let's extract a center block from this table. We want a 2 by 2 slice covering the middle of the array. We type print table underscore data underscore array square brackets 1 colon 3 comma 1 colon 3. What does this mean? The row slice 1 colon 3 includes rows 1 and 2. Note that it excludes the index 3. The column slice 1 colon 3 includes columns 1 and 2, so it picks the values at the intersection of those rows and columns. Let's run the program. You will see 50, 60, 80, 90. So we got from row 1 columns 1 and 2 50 and 60. From row 2 columns 1 and 2 80 and 90. This is how you can extract any rectangular block from a 2D array. Very useful for matrix manipulation or zooming in on specific regions. Now let's slice the second column only from all rows. We type print table underscore data underscore array square brackets colon comma 1. Let's decode this. The colon before the comma means we are selecting all rows. The one after the comma means we are selecting only column index 1, the second column. Let's run the program. You will see 20, 50, 80, 100, 10. These are the second column values from each row. This is how you isolate one column from a 2D table. Let's see how to select every second row from the array. We type print table underscore data underscore array square brackets 0 colon colon 2 comma colon. The 0 colon colon 2 part means start from row index 0, go until the end and step by 2. So this gives us row 0 and row 2. The comma colon part means include all columns. Let's now run the program and look at the output. You will see 10, 20, 30, 70, 80, 90. That's exactly what we expected. Every alternate row starting from the top. This technique is useful when you want to sample or downsample your data vertically. Now let's slice the last two rows using negative indexing. We type print table underscore data underscore array square brackets -2 colon comma colon. Here's how it works. -2 colon tells NumPy to start from the second to last row and go till the end. Comma colon again means include all columns. Let's run the program. And the output will be 70, 80, 90, 100, 100, 10, 100, 20. That's row 2 and row 3, the last two rows of our array. This approach is especially helpful when you want to look at the bottom part of your data, such as recent entries or footer rows. Now let's extract the first two columns from all rows. We type print table underscore data underscore array square brackets colon comma 0 colon 2. The colon before the comma means all rows. The 0 colon 2 after the comma means select column index 0 and 1. That's the first two columns. Let's run the program and see what we get. Output 10, 20, 40, 50, 70, 80, 100, 100, 10. We have now sliced off the last column and kept just the first two. This is helpful when you want to ignore irrelevant columns and focus on the key ones. This is all about slicing 2D arrays in NumPy. In this lecture, we will learn data types in NumPy. Understanding NumPy data types is essential, especially when you are dealing with large datasets and need efficient memory usage or precision control. In NumPy, every array has a property called type, short for data type. It tells you what kind of data is stored in that array. It could be integers, floating point numbers, strings, or even booleans. The beauty of NumPy is that it's highly optimized, and part of that optimization comes from using homogeneous arrays. That means all items in a NumPy array must have the same data type. Now let's see how to work with different data types using NumPy. Let's first create a new Python file. Right-click on your folder, click on New, then choose Python file. Let's name the file numpy_data_types. Now we'll start by importing NumPy. This imports NumPy and gives it the nickname NP, which is the standard convention. Let's create an array with integers. We type integer_array equals np.array, followed by within square brackets 1, 2, 3, 4. To print the array, we type print within parentheses integer_array. To check the data type, we type print within parentheses integer_array dot dtype. Let's run the program and see the output. This shows the array contains integer data, int 32 or int 64 depending on your machine. So we learned that NumPy automatically assigns dtype based on values. Now we'll create an array with decimal values. We type float_array equals np.array within square brackets 1.1, 2.2, 3. Then we type print within parentheses float_array and next print within parentheses float_array dot dtype. Let's run the program. You can see the output says float 64. That means each number is stored using 64-bit floating point precision. It's useful when you need accuracy in calculations. Let's now create an array of strings. We type names_array equals np.array within square brackets in double quotes Alice, Bob, Charlie. Now let's print it. Print within parentheses names_array and then print within parentheses names_array dot dtype. Run the program and you'll see a dtype like U7, which means Unicode string with 7 characters. NumPy chooses the longest string and allocates that size across the entire array. Let's now use Boolean values true and false. We type bool_array equals np.array within square brackets true, false, true. Then type print within parentheses bool_array and next print within parentheses bool_array dot dtype. Let's run the program. The output here is the dtype bool. The array contains only Boolean values. This is especially useful when performing conditional filtering. Let's create a number array, but manually set the data type to float. We type convert_float_array equals np.array within square brackets 10, 20, 30, day type property followed by equals and then np.float64. Then print the array. Print within parentheses convert_float_array and again print within parentheses convert_float_array dot type. Let's run the program and you will notice that NumPy has converted the integers into decimal format like 10.0, 20.0 and so on. This is a way to control precision or standardize the dtype in advance. Next, if you want to know how much space each element occupies, use item size property. Let's print memory usage for integer and float arrays. We type print within parenthesis integer underscore array dot item size, and print within parenthesis float underscore array dot item size. Let's run the program. The output will tell you the number of bytes per item. For example, 8 bytes for int64 and 8 bytes for float64. This is very useful when you are working with millions of elements and care about memory. So to summarize, NumPy supports various data types like integers, floats, strings, and booleans. Each array has a consistent dtype, meaning all elements must be of the same type. You can inspect dtype using .dtype and check memory size using .item size. You can also force the data type when creating an array using the dtype parameter. Mastering data types helps you write faster, cleaner, and memory efficient NumPy code. Thanks for watching. I will see you in the next one. Hi everyone, welcome back. In this lecture, we'll talk about one of the most useful properties in NumPy called array shape. Every NumPy array has a built-in property called shape. This tells us how many rows and how many columns the array has. Shape is important when working with multidimensional arrays, especially in data science and machine learning. Let's jump into PyCharm and understand this step by step with examples. Right-click on NumPy folder, choose New, then select Python file. Let's give it a name, NumPy underscore array underscore shape. Now at the top, let's import NumPy using the standard syntax. We type import NumPy as np. This imports NumPy and gives it the alias np. Let's first create a one-dimensional array. We type 1 underscore d underscore array equals np.array within square brackets 5, 10, 15, 20. Now let's print the array. We type print within parenthesis 1 underscore d underscore array, and then to check the shape, print within parenthesis 1 underscore d underscore array dot shape. Let's run the program. Since this is a one-dimensional array with 4 elements, the shape will be displayed as 4. This means 4 items in a single row. Let's now define a two-dimensional array with 3 rows and 2 columns. We type 2 underscore d underscore array equals np.array within square brackets. Then create subarrays for rows. Within square brackets 1, 2, within square bracket 3, 4, within square bracket 5, 6, and finally close the outer square bracket. Now let's print this array. We type print within parenthesis 2 underscore d underscore array, and then print within parenthesis 2 underscore d underscore array dot shape. Let's run the program. You will see the output is open parenthesis 3, 2 close parenthesis, which means 3 rows and 2 columns. This shape helps NumPy understand how to organize and manipulate the data. Let's now create a 3D array, which means multiple 2D arrays stacked together. We type 3 underscore d underscore array equals np.array within square brackets. Then define two two-dimensional matrices. First is within square brackets 1, 2, within square brackets 3, 4. Second is within square bracket 5, 6, within square brackets 7, 8. Now close the outer square bracket. Now let's print it. Print within parenthesis 3 underscore d underscore array. And to get the shape, print within parenthesis 3 underscore d underscore array dot shape. Let's run the program. You will get the output open parenthesis 2, 2, 2 close parenthesis. That means 2 blocks of 2D arrays, each with 2 rows and 2 columns. This is extremely useful when working with color images, video frames, and advanced data formats. So to summarize, the shape property in NumPy shows the structure of an array like how many rows, columns, and dimensions it has. This helps you visualize, transform, and validate your data, especially when working with datasets, models, or images. Always check shape before applying operations like reshape, transpose or broadcasting. Thanks for watching. I will see you in the next one. In this lecture, we are going to explore a powerful NumPy feature called reshape. Reshaping means changing the shape of an array. When we reshape an array, we are not changing the data. We are just changing how it's laid out in rows and columns. For example, we can take a simple one-dimensional array and turn it into a matrix with rows and columns, or even reshape it into a three-dimensional block of data. This is super useful when you are working with images, matrices, or even machine learning models where the shape of your data matters. So let's now open PyCharm and walk through everything step by step. Right click on NumPy folder. Choose new and select Python file. Let's give it a name, numpy_array_reshape dot. Now let's import NumPy at the top. We type import NumPy as np period. Now let's begin with a basic one-dimensional array. We'll first create a simple one-dimensional array with 6 elements. We type original_array equals np.array within square brackets 1, 2, 3, 4, 5, now print it. Print within parenthesis original_array. Also print the shape. Print within parenthesis original_array dot shape. Now let's run the program. This is a 1D array, 6 elements in a single row. Shape will show as open parenthesis 6, close parenthesis. It means it has 6 elements. Now let's reshape it into 2 rows and 3 columns. We type reshaped_array equals original_array dot reshape within parenthesis 2, 3. Then print the reshaped array. Print within parenthesis reshaped_array and also its shape. Print within parenthesis reshaped_array dot shape. That's it. We've now turned a flat array into a matrix with 2 rows and 3 columns. When we run this program, the original array prints as 1, 2, 3, 4, 5, 6, and the shape shows open parenthesis 6, close parenthesis, meaning it's one long row of 6 elements. The reshaped version prints like this: 1, 2, 3 as first row, 4, 5, 6 as second row, and the shape now becomes 2, 3, which means 2 rows, 3 columns. The data is unchanged, but the layout is different. Let's now take the same array and reshape it into 3D. We type reshaped_3_d equals original_array dot reshape within parenthesis 2, 1, 3. Then print it. Print within parenthesis reshaped_3_d and also its shape. Print within parenthesis reshaped_3_d dot shape. This tells NumPy, I want 2 blocks each with 1 row and 3 columns. Let's run the program. We can see a 3D structure printed and the shape shows as 2, 1, 3. Now the question is, what happens if the size doesn't match? Let's say you try to reshape the original array of 6 elements into something like 4 by 2. We type invalid_reshape equals original_array dot reshape within parenthesis 4, 2. Then print it. Print within parenthesis invalid_reshape. This will raise an error because 6 elements cannot be reshaped into 8 positions. So always remember, the total number of elements must stay the same. Now here's a trick. If you don't know one of the dimensions, you can tell NumPy to calculate it automatically using -1. We type auto_reshape equals original_array dot reshape within parenthesis 2, -1. Here NumPy will figure out how many columns are needed to fit the 6 elements into 2 rows. Next, print it and test it. Print within parenthesis auto underscore reshape, and also its shape. Print within parenthesis auto underscore reshape d dot shape. Let's run the program. NumPy sees that we have 6 elements and one dimension is 2. So it figures out the other dimension must be 3. You will get the same result as 2 by 3. This feature is super handy when working with unknown dimensions. So to summarize, reshaping is used to change the structure of the array without changing its data. You can reshape from 1 dimension to 2 dimensions or 2 dimensions to 3 dimensions as long as the total number of elements stays the same. Use the dot shape to check the dimensions and use -1 when you want NumPy to auto calculate. Thanks for watching. I will see you in the next one. Hi everyone, welcome back. In this lecture we are going to learn how to iterate through NumPy arrays. Iteration simply means going through each element one by one using a loop. And the good news is we can iterate over 1 dimension, 2 dimension, and even 3 dimension arrays using the exact same concept. Let's open PyCharm and begin coding step by step. Right click on the NumPy folder, choose new, then Python file. Let's name it NumPy underscore iterate underscore arrays. Now let's start by importing NumPy. We type import NumPy as np. Okay. Let's now begin with a 1D array example. Let's create a simple array of numbers. We type numbers underscore array equals np dot array within square brackets 10, 20, 30, 40. Now we want to go through each element one at a time. We use a for loop. We type for keyword followed by variable number in keyword numbers underscore array colon. Inside the loop, print within parenthesis pass number. That's it. We are now iterating over a one-dimensional array. Let's run the program and see the output. 10, 20, 30, 40. Each number printed on a new line one by one. Now let's move to a two-dimensional array. Imagine it like a table with rows and columns. We type table underscore array equals np dot array within square brackets open square bracket 1, 2 close square bracket comma open square bracket 3, 4 close square bracket. This gives us a 2 row by 2 column matrix. Now let's loop through it. We type for keyword followed by variable row in keyword table underscore array colon. Then inside the loop print within parenthesis row. When we run this, the output will be 1, 2 as row 1, 3, 4 as row 2. Here each row is treated as a one-dimensional array. Now if you want to print every individual number, you need a nested loop. We type for keyword followed by variable row in keyword table underscore array colon. Next inside create one more for loop. For keyword followed by variable name item in keyword row colon. Next print it. Print within parenthesis item. When we run this, the output 1, 2, 3, 4. Now we are accessing each element of the two-dimensional array one by one. Perfect. Let's now go a step further and try a three-dimensional array. We type 3 underscore d underscore array equals np dot array within square brackets within square brackets within square bracket 1, 2 within square brackets 3, 4 next block within square brackets 5, 6 within square brackets 7, 8. Make sure to close all the square brackets properly. This creates a 3D array with 2 blocks. Now we loop through it using nested loops. We type for keyword followed by variable block in keyword 3 underscore d underscore array colon. Next let's create a nested for loop for keyword followed by variable row in keyword block colon. Next within this for loop create one more for loop. Type for keyword followed by variable item in keyword row colon. Print within parenthesis item. Let me explain this nested loop properly. In the first for loop, we loop through each block within the three-dimensional array. Each block is basically a 2D array inside the 3D structure. For example, if the array has 2 blocks, we go one at a time. Now inside that outer loop, we go one level deeper for row in block colon. This loop now goes through each row present in the current block. So from a 2D matrix, we are now picking rows, which are 1D arrays. Finally, inside that loop, we go even deeper for item in row colon. Now we are picking individual numbers inside that 1D row. So for each row, we'll go item by item. Inside this innermost loop, we simply print the value. This structure will print every single number inside the 3D array one by one. Now let's run the program. The output is 1, 2, 3, 4, 5, 6, 7, 8. You will see a sequence of numbers printed. All the values that exist inside that multi-dimensional array printed line by line. This is a very common pattern when working with multi-dimensional arrays in NumPy, especially when you need to access or manipulate every value inside. Now let's see editor function from NumPy to iterating arrays. It stands for NumPy iterator, and it allows us to loop through each element of a NumPy array no matter how many dimensions it has. This means whether you have a one-dimension array like a list, a two-dimension array like a table, or a three-dimension array like a cube, you can use editor function to go through all the values one by one. Normally, for multi-dimensional arrays, we'd use nested loops, one loop inside another, but with editor function, we only need one simple loop. It handles all the complexity behind the scenes. Let's understand this with an example. Suppose we have a two-dimensional array of student marks. We'll call it student underscore marks underscore table underscore array. We define it as create a variable called student underscore marks underscore table underscore array equals NumPy dot array. Within parentheses, define a list of lists. Each list represents a row like this. Inside square brackets, 85, 90, 95. Another row, 88, 92, 96. So we have a 2 by 3 array, 2 rows, 3 columns. Now to loop through all values using editor function, we say for keyword followed by variable score in keyword and then np dot call the editor function and the passing the student underscore marks underscore table underscore array. Next, print the score. Print within brackets score. That's it. Let's now run the program and look at the output. 85, 90, 95, 88, 92, 96. All values printed one by one, even though the original array was in a 2-row format. That's the power of editor. It flattens the process of looping just one loop, and it goes through all 6 elements from the first row to the last, left to right. Let me give you 3 reasons why this is awesome. First, simplicity. You don't have to worry about how many dimensions your array has. Whether it's 1D, 2D or 10D, you use the same loop. Second, readability. Your code becomes cleaner, easier to understand and easier to maintain. And third, performance. Editor is optimized for speed under the hood, which helps when dealing with large datasets in real-world projects. Alright, before we wrap up, let's quickly go over what we learned in this lecture. We started with a one-dimensional array and saw how easy it is to loop through it using a simple for loop. One by one, each number is printed, just like a shopping list, reading each item line by line. Then we stepped up to a two-dimensional array, which is like a table with rows and columns. We learned how to loop over each row and then go deeper to print each value inside those rows using a nested loop. After that, we moved on to a three-dimensional array. This one is like a cube with blocks, rows and items. And again, using 3 nested loops, we printed every single element from the 3-dimensional structure step by step. Finally, we introduced the undeter function from NumPy. This is a super convenient way to go through any array, whether it's 1-dimensional, 2-dimensional or 3-dimensional, without worrying about how many loops to write. Just plug it into a for loop and you are good to go. Thanks for watching. I will see you in the next one. Hi everyone, welcome back. In this lecture, we are going to learn how to join NumPy arrays together. Joining arrays simply means combining 2 or more arrays into one. And NumPy makes this really easy, using functions like concatenate, stack and hstack. Let's open PyCharm and begin step by step. Right click on the NumPy folder. Choose new, then Python file. Let's name it numpy_join_arrays. Let's begin by importing NumPy. We type import NumPy as np. Now let's create 2 simple arrays to work with. We type array_1 equals np.array within square brackets 10, 20, 30. Then next line array_2 equals np.array within square brackets 40, 50, 60. Let's print both arrays to see them. We type print within parenthesis array_1, print within parenthesis array_2. Now we'll join these 2 arrays using np.concatenate function. So we type joined_array equals np.concatenate within parenthesis inside square brackets array1, array2. Then print it, print within parenthesis joined_array. Let's run the program and see the output. We get 10, 20, 30, 40, 50, 60. Perfect. We have successfully combined both arrays into a single 1-dimensional array. Now let's try joining 2D arrays or 2 small tables. We type matrix_1 equals np.array within square brackets open square bracket 1, 2 close open square bracket 3, 4 close. And for the second one, matrix_2 equals np.array open square bracket 5, 6 close open square bracket 7, 8 close. Let's print both matrices. Print matrix1, print matrix2. Now let's join them vertically, one below the other. That means row wise. We use concatenate again. We type joined_matrix_vertical equals np.concatenate open parenthesis inside square brackets matrix1, matrix2, axis equals 0. Now print it. Print joined matrix vertical. When we run the program, the output will be 1, 2 as first row, 3, 4 as the second row, 5, 6 as the third row, 7, 8 as the fourth row. So the output combined both 2 row matrices into a 4-row table. Perfect. Let's now try joining column wise, which means joining side by side. We change axis from 0 to 1. We type joined_matrix_horizontal equals np.concatenate open parenthesis inside square brackets matrix1, matrix2, axis equals 1. Print it. Print joined matrix horizontal. This will give us 2 rows, 4 columns. Perfect. Each row was extended with more columns from the second matrix. You can also use stacking methods in NumPy for more flexibility. Stacking is same as concatenation. The only difference is that stacking is done along a new axis. We can concatenate 2 1-dimensional arrays along the second axis, which would result in putting them one over the other, i.e. stacking. Let's try the stack function, which stacks arrays along a new axis. We type stacked_array equals np.stack open parenthesis inside square brackets array1, array2. Now print it. Print stacked array. Let's run the program. This will give a 2D output. Each row is one of the arrays. That's stacking along axis 0 by default. We can also stack along axis 1. which joins column wise. We type stacked underscore column equals np.stack inside square brackets array 1 comma array 2 comma axis equals 1. Now print it. Print stacked column. Let's run the program. The output displays 3 rows and 2 columns. That's really useful when we want columns of values from 2 arrays. Now let's take a look into 2 special ways to join NumPy arrays: horizontal stack and vertical stack. These 2 methods, stack and reshaping, allow us to join arrays in different directions such as horizontally and vertically. Let's first combine both arrays side by side using horizontal stacking. We type edgestack underscore result equals np.edgestack within parenthesis array underscore 1 comma array underscore 2. This will join the second array to the right side of the first one. So they are placed horizontally one after the other. Now print the result. We type print within parenthesis edgestack underscore result. Let's run the program. The output will be 10, 20, 30, 40, 50, 60. So we have successfully joined the arrays side by side. This is like extending a row, adding more items in the same line. Now let's try vertical stacking. This means one array will appear on top and the other below. We type vstack underscore result equals np.vstack within parenthesis array underscore 1 comma array underscore 2. Here the two 1D arrays will be placed vertically, forming a 2D structure. It will look like rows stacked on top of each other. Let's print the result. We type print within parenthesis vstack underscore result. Let's run the program and see the output. You will get 10, 20, 30 as the first row, 40, 50, 60 as second row. That's it. We now have a 2D array with 2 rows. The first row is from array 1 and the second row is from array 2. With edgestack, the two arrays remain one-dimensional and get merged in a single row. With vstack, the arrays are stacked row by row and we get a two-dimensional array. Just remember, horizontal stack adds more columns. Vertical stack adds more rows. This is super useful when combining data row-wise or column-wise, especially in data science or machine learning pre-processing. So let's summarize what we learned. Concatenate is great for joining arrays directly along existing axes. Stack is perfect when you want a new axis, especially for turning 1D into 2D. And edgestack and vstack are handy shortcuts for column and row joining. Mastering how to join arrays is very important, especially when you are working with data that comes in parts and needs to be combined before analysis. In the next lecture, we'll learn about splitting arrays, which is the reverse process. Make sure to follow along. See you in the next one. Hi everyone, welcome back. In this lecture, we're going to learn how to split NumPy arrays. Splitting means dividing one array into multiple smaller parts. It's really useful when you want to break data into sections. We'll try splitting a one-dimensional array, a two-dimensional array row-wise and column-wise, and finally use special functions like edgesplit and vsplit. Let's open PyCharm and begin step by step. Right-click on the NumPy folder, choose New, then Python file. Let's name it NumPy underscore split underscore arrays. We type import NumPy as np. Let's begin with a 1D array example. We type numbers underscore array equals np.array within square brackets 10, 20, 30, 40, 50, 60. Print it. Print within parenthesis numbers underscore array. Now let's split it into 3 equal parts. We type split underscore result equals np.array underscore split. Pass numbers underscore array, 3. This divides the array into 3 equal parts. Each new part becomes a subarray. Now loop through the result and print each chunk. We use a for loop. Let's type for keyword followed by variable part. In keyword split underscore result colon inside the loop. Print part. Let's run the program. You'll see 10 to 20, 30 40, 50 60. 3 arrays, each holding 2 values. Perfect. Now we have successfully split the one-dimensional array into 3 equal parts. Now let's try with a two-dimensional array. We imagine this like a table with 4 rows and 3 columns. We type table underscore data underscore array equals np.array within square brackets. Inside that, within square brackets 1, 2, 3, comma, within square brackets 4, 5, 6, comma, within square brackets 7, 8, 9, comma, within square brackets 10, 11, 12. Print it, print table underscore data underscore array. Now let's split it into 2 equal row blocks. We type row underscore chunks equals np dot array underscore split. Pass table underscore data underscore array comma 2. Note that the 2 means we split the array into 2 equal parts. Next, let's loop through it. We type for keyword followed by row underscore part. In keyword row underscore chunks colon inside the loop. Print row underscore part. Let's run the program. We get 2 chunks each containing 2 rows. Note that it splits row-wise by default, so you do not need to specify the access attribute. That means the array is divided along the rows, so you are cutting horizontally. Each resulting subarray will contain a set of rows from the original array. Now we have successfully split the two-dimensional array into 2 equal parts row-wise. Let's now split this 2D array column-wise. This time we specify an access. We type column underscore chunks equals np dot array underscore split. Pass table underscore data underscore array, comma, 3 comma access equals 1. Now use a loop. We type for keyword followed by column underscore part. In keyword column underscore chunks colon. Inside print column underscore part. Let's run the program. You will now see 3 outputs, each showing a single column across all rows. Perfect column split. Note that if you want to split column wise, you must explicitly specify that the access is equal to 1. Now we'll focus on 2 specific methods, addSplit and vSplit in NumPy. These are shortcut methods provided by NumPy to split 2-dimensional arrays either horizontally or vertically depending on your needs. Let's understand both one by one using our table data array. Now imagine your array as a spreadsheet with multiple columns. If we want to split it column wise, meaning horizontally, we use the addSplit method. We type addSplit underscore result equals np.addSplit and inside parenthesis pass table underscore data underscore array comma 3. That tells NumPy take this array and split it horizontally into 3 equal column chunks. Now to print each piece separately, we use a loop. We type for keyword followed by variable h underscore part. In keyword addSplit underscore result colon. Inside the loop we write print and then inside parenthesis h underscore part. Let's now run this and see the output. As you can see, each part is now a separate subarray but only one column wide and includes all the rows. So this is a column wise horizontal split. Make sure that the number of columns in your original array is divisible by the number you pass. In this case 3 columns. Otherwise NumPy will raise an error. Perfect. Now let's move to the vertical split. This time we want to cut the array row wise from top to bottom, just like slicing a cake horizontally. We use the vSplit method for this. We type vSplit underscore result equals np.vSplit and inside parenthesis table underscore data underscore array comma 2. This tells NumPy take the full table and split it vertically into 2 equal row chunks. Now to print the 2 parts, we type for keyword followed by variable we underscore part. In keyword we split underscore result colon. Inside the loop we print and inside parenthesis v underscore part. Now let's run this section. As you can see, now we have two separate arrays, each one containing 2 rows from the original array, but with all the 3 columns intact. This is how vertical splitting works. And that's how you use hsplit and vsplit to quickly break down a 2-dimensional NumPy array, column-wise or row-wise. Let's quickly recap. We learned how to split arrays using array underscore split, hsplit and vsplit. You can split 1-dimensional arrays into equal parts or split 2-dimensional arrays, either row-wise or column-wise. These techniques help break down large datasets into smaller, manageable chunks. In the next lecture, we'll explore searching values inside arrays. That's it for now. Thanks for watching and keep learning. Hi everyone, welcome back. In this lecture, we're going to learn about searching arrays in NumPy. Now, what do we mean by searching? It simply means finding the positions of certain values or locating which elements satisfy a particular condition. And NumPy makes this incredibly simple with some powerful methods. NumPy provides the where method to search an array for a certain value and return the indices that match. There is a method called search sorted, which performs a binary search in the array and returns the index where the specified value would be inserted to maintain the search order. Let's get started step by step. Right click on the NumPy folder, choose new then Python file. Let's name it NumPy underscore search underscore arrays. Now open the file. Let's start by importing NumPy. We type import NumPy as np. Let's now create an array of numbers. We type numbers underscore array equals np dot array and within square brackets 10, 20, 30, 40, 50, 60, 70. To make sure it looks right, let's print it. We type print within parenthesis numbers underscore array period. When we run this, the output will be a simple 1-dimensional array with 7 numbers. Now let's say we want to find where the value 40 exists. We type result underscore 40 equals np dot where inside parenthesis numbers underscore array double equals 40. This means check where the value is 40. It will return the index positions that match this condition. Let's print the result. We type print and inside parenthesis result underscore 40. When we run it, the output will be array of single index position 3. This tells us the value 40 exists at index position 3. Now let's search where values are greater than 35. We type greater underscore than underscore 35 equals np dot where inside parenthesis numbers underscore array greater than 35. Then print the result. Print within parenthesis greater than underscore 35. This gives index positions 3, 4, 5, 6. So all values from index 3 onwards, which are 40, 50, 60 and 70, satisfy the condition. Now let's create a simple array that contains repeated values. We type exam underscore scores equals np dot array and inside square brackets 1, 2, 3, 4, 5, 4, 4. Let's now print this array to see it clearly. We type print and inside parenthesis exam underscore scores. When we run this, the output shows all the elements. This array has multiple 4s in it at different positions. Now let's see how to find all indexes of value 4. Let's use np dot where method to find where the value 4 occurs. We type positions underscore of underscore 4s equals np dot where inside parenthesis exam underscore scores double equals 4. This will return all index positions where the value is exactly 4. Let's print it. We type print and inside parentheses positions underscore of underscore 4. This gives us array index positions 3, 5, 6. That means the value 4 is found at index 3, index 5 and index 6. Let's now check which elements in another array are even. We type all underscore numbers equals np dot array and inside square brackets 1, 2, 3, 4, 5, 6, 7, 8. To find where numbers are even, we use even underscore indexes equals np dot where and inside parentheses all underscore numbers modulo 2 double equals 0. Then print inside parentheses even underscore indexes. The output is array of index positions 1, 3, 5, 7. So even numbers are at index 1, 3, 5 and 7, which means values 2, 4, 6 and 8. Next we can do the same for odd numbers. We type odd underscore indexes equals np dot where inside parentheses all underscore numbers modulo 2 double equals 1. And then print inside parentheses odd underscore indexes. The output is array of index positions 0, 2, 4, 6. So the odd numbers 1, 3, 5 and 7 are at index 0, 2, 4 and 6. Now let's learn something new. Let's say you want to insert a value into a sorted array and you want to know where it should go. That's what np.searchSorted is for. Let's create a new array. We type sorted underscore data equals np.array and inside square brackets 6, 7, 8, 9. Let's say we want to insert 7 and we want to know the correct index. We type insertion underscore point equals np.searchSorted and inside parentheses sorted underscore data comma 7. Let's print this. Print inside parentheses insertion underscore point. The output is 1, which means if you insert 7 at index 1, the array will remain sorted. This is very useful in binary search and sorted insertions. Let's quickly review what we learned today. We used np.where to find positions of a specific value, search for even and odd numbers, combine conditions using modulo. And we used np.searchSorted to find the correct index where a value should be inserted, ensure that the array remains sorted after insertion. Thanks for watching and I will see you in the next lecture. Hi everyone, welcome back. In this lecture we are going to learn how to sort arrays using NumPy. Sorting is one of the most common operations you will perform on data, whether it's scores, names or values in a dataset. And NumPy gives us a very easy and fast way to do this. Let's get started with some examples. In PyCharm, let's create a new Python file. We'll name it NumPy underscore sort underscore arrays. Now at the top of the file, type import NumPy as np. This allows us to use all NumPy functions in a short form. Let's first create a simple one-dimensional array. We type unsorted underscore numbers equals np.array and inside square brackets 5, 2, 9, 1, 7. Note that the elements are not sorted in the array. Next, let's print this array before sorting. Print inside parentheses the string original array, comma, unsorted underscore numbers. Now let's use np.sort method to sort the array. Let's type sorted underscore numbers equals np.sort and inside parentheses unsorted underscore numbers. Let's print the result. Print the string sorted array, comma, sorted underscore numbers. Let's run the program and see the output. Original array 5, 2, 9, 1, 7. Sorted array 1, 2, 5, 7, 9. So you can see NumPy returns a new sorted array. The original one remains unchanged Now we have successfully sorted a simple one-dimensional array. Let's now try sorting a two-dimensional array, a matrix. We'll sort it row by row. We type matrix underscore scores equals np dot array and inside two levels of square brackets. First row 3 1 2, second row 6 4 5. Then print the string original 2D array matrix underscore scores. Now let's write the logic to sort the matrix. So type sorted underscore matrix equals np dot sort and inside parentheses matrix underscore scores. Next, let's print the sorted array. Print the string sorted 2D array sorted underscore matrix. Let's run it. You can see the output. Original 2D array, sorted 2D array. In a sorted 2D array, you can see that each row is sorted in ascending order. By default, np.sort method sorts row by row. Each row is treated as a separate 1D array. Now we have successfully sorted a simple two-dimensional array row by row. If you want to sort column by column, you need to set an axis. Let's explore this as well. We type column underscore sorted equals np.sort and inside parentheses matrix underscore scores comma axis equals 0. Then print the string column wise sorted array column underscore sorted. Let's run the program. You can see the output. Wait, that didn't change because our original values are already in increasing order column wise. Let's try with a better example. We update our matrix to matrix underscore scores equals np dot array. First row 30, 10, 40. Second row 20, 50, 15. Now let's sort column wise. We type column underscore sorted equals np dot sort and inside parentheses matrix underscore scores comma axis equals 0. Then print the string column wise sorted array column underscore sorted. Let's run the program. You can see the output. Column wise sorted array, first column 20 30, second column 10 50, third column 15 40. Each column was sorted independently from top to bottom. Now we have successfully sorted a two-dimensional array column wise. Sorting isn't just for numbers. NumPy can also sort strings alphabetically. Let's type student underscore names equals np dot array and inside square brackets Zara, Arjun, Meena, Amit. Now sorted underscore names equals np dot sort and inside parentheses student underscore names. Then print sorted underscore names. The output is Amit, Arjun, Meena, Zara. It sorts them in alphabetical order just like words in a dictionary. Let's quickly review everything we covered in this lecture. We explored how to sort arrays using NumPy's sort function. And here's what we learned. We sorted one-dimensional arrays and saw how the numbers were arranged in ascending order. We then moved on to two-dimensional arrays. We sorted them row by row using the default behavior. We also learned how to sort column by column by using the axis parameter setting axis equals 0. Next, we sorted an array of strings alphabetically, just like names in a contact list or words in a dictionary. Sorting helps organize and prepare data, and it's a must-know skill in a real-world data science project. You're doing great so far. Keep going. Hi everyone, welcome back. In this lecture, we are going to learn how to filter arrays using NumPy. Filtering means selecting only the elements that meet a certain condition. It's a powerful technique used in data science to clean, sort, or extract meaningful information. Let's open PyCharm and get started step by step. Right-click on the NumPy folder. Choose New, then Python file. Let's name it NumPy underscore filter underscore array. Now at the top of the file, we import NumPy. We type import NumPy as NP. Perfect. Let's say we have a list of ages. We want to filter out the people who are above 18. Let's create that array. We type ages underscore array equals np.array and within square brackets 12, 17, 19, 21, 15, 18, 22. So now we have a list of 7 ages. Some are above 18, some are not. Let's print the full array first. We type print inside parentheses ages underscore array. Let's run the program and see the output, the array with all the elements. Now we want to filter out the ages above 18. We can apply a condition directly on the array. We type above underscore 18 equals ages underscore array greater than 18. This will create a boolean array with true where the age is more than 18 and false otherwise. Let's print this boolean array. We type print inside parentheses above underscore 18. Run the program and you will see false, false, true, true, false, false, true. This tells us that the 3rd, 4th and 7th values are above 18. Now here comes the magic. We pass the boolean array inside square brackets right after the original array. This filters out only the true positions. We type filtered underscore result equals ages underscore array inside square brackets above underscore 18. Then print it, print inside parentheses filtered underscore result. When we run this, the output will be 19, 21, 22. Beautiful. We filtered all values greater than 18 from the original array. Let's now try another filter, but this time directly in one line. We type even underscore numbers equals ages underscore array inside square brackets ages underscore array modulus 2 equals 0. This condition checks for even numbers. Let's print the result. Print inside parentheses even underscore numbers. Let's run the program and you can see the output 12, 18, 22. Nice. We have filtered all even ages from the original array. Now let's filter the odd numbers. We type odd underscore numbers equals ages underscore array inside square brackets ages underscore array modulus 2 equals 1. Then print the result. Print inside parentheses odd underscore numbers. Let's run the program. You can see the output 17, 19, 21, 15. All are odd numbers. That's how we filter odd numbers from an array using just one line. Now we will see a real world use. Filter scores above passing marks. Let's say we have scores from a test and we want to filter the students who scored more than 40. We type scores underscore array equals np.array inside square brackets 25, 45, 32, 78, 60, 39. Now we have a one-dimensional array. Next, let's filter the students who scored more than 40. Let's type past underscore students equals scores underscore array inside square brackets scores underscore array greater than 40. Next, print the result. Print inside parentheses past underscore students. Let's run the program and you can see the output 45, 78, 60. All the marks are above 40. It's simple and clean, right? This filtering technique works for any condition, even complex ones. Let's recap. In this lecture, we learned how to filter arrays using conditions in NumPy. We used Boolean arrays to pick only the elements that match our condition. We filtered ages above 18, even and odd numbers, students who passed based on scores. Filtering lets you quickly select useful data from large datasets in just one line of code. Let's now move on to the next lecture.